Yeah, hello everyone. Um, co-host, can you please confirm that you can listen me or not?
Yeah, yes, sir, you are audible.
Okay. So yeah. So let me figure it out first. So mm, just back. So let me share the screen and start from the place where we left. So it was all dependent on the things that we were doing in the last class. So just a minute, let it go first. So, right. So, so the plan was basically to first make you aware with a lot of things regarding answers. And the electrical vehicle was the first module that started initially. Uh, and that was the thing that actually laid out the foundation for this course. So it all started with electrical vehicles, EVs. And once that got accelerated, or so it wasn't taken by me, but one of the other associates took that first part of the course, where thing was he actually laid out the foundation of what is an electrical vehicle and what is its significance. Told you about a lot of things related to that, and probably uh, told you how to design one and what are the key components that are being used into an electrical vehicle. So yeah, those kinds of stuffs were actually incorporated into the first part of the course. Then the second part of the first course of the electrical vehicle was the technical understanding of the same. What was the technical expertise that was being involved in order to design an electrical vehicle, and what was the necessity of an electrical vehicle and how it is important or superior, you can say, that is compared with the IC engine vehicles that are being present in the market today. So those were the key components that were actually taken into consideration for the same. Uh, there were a lot of technical expertise, technical. I don't think he might have touched upon the numerical and design part of it. If you want to do it, uh, there is another course related to electrical vehicle that was taken by me. It was 40 hours course, which would give you a brief understanding about the same and help you understand the things in a proper way. But in this course, yeah, and after that comes the experimental or operational part. So experimental was not directly possible as we are working on a remote setup on online meeting. So the only experimental part that we could actually assist you with was basically the computational part. So in the computational part, what we actually wanted to make you understand was to set up a problem onto ANSYS uh, regarding the electrical vehicles, which would actually help you understand the basic four key line principles of the same. And once you are uh, done with the technical expertise of the same, you can actually do the analysis and onto answers and tell yourself that electrical vehicles, if you designed aerodynamically properly, gives you a better endurance and performance. So uh, that was something which was key insightful. So what we did initially, so from there I took up and we actually decided to first understand what are the key principles and the methodologies that we are going to implement in the later stage are required for a proper understanding of the same. So we did the mesh conversion study analysis, curving analysis, and all these kinds of stuff. So we actually basically did a lot of things related to this, and the key parameters in our understanding was not only to help you get an understanding or feel about the same, but also to uh, apply this answers with the proper understanding. So uh, we did the mixed conversion study. We did the different aerodynamic drag comparisons of different bodies, and then we came to two different types of electrical vehicles that were actually designed here in the class. And thereafter designing, we cut it to symmetry plane and actually did the aerodynamic analysis of the same, passing the air velocities and uh, doing the further aerodynamic analysis. So, in that understanding, we came to a conclusion wherein we could actually conclude, or maybe we could assess, or maybe we could say that uh, better aerodynamic design actually gives you a better performance. So, this is not a hidden fact that design which is basically uh, help you to understand the proper problem should be better in all the methodologies or performance check parameters, which include aerodynamics. So aerodynamics was the part which we actually discussed into the class forum. So yeah, that was basically pretty much about the electrical vehicles that we kind of concluded. In the coming classes, we will be doing the same for the aerial autonomous vehicle because the second part of the coursework was basically the autonomous vehicle. So, in the second part of the course, which we started from one or two classes back, was to actually get an introduction and feel about the autonomous vehicles, and then uh, compare between the aerial autonomous vehicle and ground autonomous vehicle, and thereafter give you a brief understanding of comparison based between the two to help you understand that which one is better. So, not to basically tell you which one is better, is to make you understand the one which is actually more useful in today's world. So, aerial autonomous vehicle is the one that we also call drones, which are majorly used in today's periphery. And it plays a very vital role in basically helping you understand the complete scenario base. And uh, so yeah, that's what we'll be doing. So we'll be doing an analysis of that, and then comes the propulsion based on which we. So in the autonomous vehicle, ground autonomous vehicle also, we select the motors, right? So we have to have an understanding of how much of torque requirement is being there. So if you design an electric vehicle into Simulink or any MATLAB tool, which I don't think in this class we'll be able to complete, but just to give you a periphery of understanding so that you can discuss later or maybe study later, is to get a torque parameter that this much of the torque is basically required to basically function your autonomous vehicle, your electric vehicle. So to select the motor based on that torque basis is the key parameter. So you get a torque requirement, and then you test the torque requirement with a propeller to match that torque, and then thereafter you get the power output, mechanical and electrical power, based on which you select the motor. So it's a cross loop analysis wherein you do the same thing again and again to actually get a comparative analysis of the motor study that we'll be doing. So that's how you basically do the stuff. And that we'll be doing in the uh, second analysis that we are planning for the autonomous vehicle, for the transient analysis of a propeller for the motor selection parameter procedures. So yeah, there's a nice slide we actually completed in the last class for the autonomous vehicle. This will be the 10th slide that we'll be discussing in today's lecture. So, in the 10th slide, we're discussing basically about planning and control. So the brains of autonomy. So basically, yeah, that is true. That if you plan and control properly, these are the two key parameters that are needed for a proper smooth functioning of the autonomous vehicle. Because in an autonomous vehicle, that is the only thing that is being required to function it properly. So The autonomous vehicle is the one which basically defines autonomy and helps to understand that the brain is functioning properly. So uh, basically, you'll be getting the key understanding of the same once and only after uh, your understanding about the autonomous vehicle becomes clear. So your brain and your planning. The planning and control are the basic controlling parameters for defining the uh, autonomy of the vehicle. So yeah, the first part was the route planning. So okay, so route planning. Yeah. So so yeah, the autonomous driving system processes information through a hierarchical planning and control architecture, operating at different frequencies for optimal decision making. So that is true that autonomous driving vehicles processes information through a very sequential manner or a hierarchical manner for planning and control architecture, operating at different frequencies for optimal decision making. True. So route planning. First comes the route planning. So the route on which the autonomous vehicle has to go has to be decided first only so that during the motion of the vehicle, it becomes easier for moving from point A to point B. So, uh, determining the optimal high-level paths from origin to destination, considering global map data and traffic conditions. So, decision sequence is seconds to minutes. So, this is a global level of the brain autonomy. So, there are global level and local level. So, local levels are the one that needs to be addressed on a very immediate basis, and global level are the one that if the local level gets taken care by, the global level gets automatically taken care of. So the global levels are the one that actually defines the complete system. Okay, so route planning. So route planning is clear. So in the route planning, so global level is the route planning, wherein you actually define your path from point A to point B, that is your origin to destination being defined first, and considering global map data and traffic conditions. So these are dynamic parameters, right? So the global map and traffic conditions are the ones that actually changes with time. So uh, this uh, actually gets defined from time to time. So the map data and traffic conditions are the ones that changes. So it gets updated and the route planning gets optimized. The second, so this is the global level optimization part. And the second one is the behavior planning. So decide on tactical maneuvers like lane changes, turns, and interactions with other road users, adapting to dynamic environments. Decision is frequency. Decision frequency is seconds. So it becomes very fast and the maneuverable the maneuverable points are very dynamic in nature because when you go on a road and decide your plan from point A to point B, that takes amount of time. So that time, your nature of the traffic, the nature of the lane changes requirement becomes different. But then when you go on a very busy timing schedule, that times it becomes very different. So it's totally dependent on various other conditions that are dynamic in nature. So that actually governs or controls your complete behavior planning methodology. So that is the second global level optimization point. Third is the trajectory generation. So it creates a smooth collision-free path for the vehicle to follow in the immediate future, updating continuously. So decision frequency is milliseconds. So trajectory generation. So it creates a smooth collision-free path for the vehicle to follow in the immediate future, updating continuously. Decision frequency is milliseconds. So that is true. So trajectory generation is basically uh, the one that actually creates a very smooth and so whenever you want to go from point A to point B, you actually define a trajectory or define a route map or define the route map is global, but trajectory generation is very dynamic. generates and updates based on the dynamic behavioral plannings and route plans. So you see how dynamic local variables are getting controlled, and it affects the global variables as well. So trajectory planning is a dynamic path planning methodology which actually governs a lot of other global parameters. So creates smooth collision-free paths for the vehicle to follow in the immediate future, updating continuously. Decision frequency is milliseconds. Then the next one is low-level control. So low-level control is basically executing precise commands to the vehicle actuators, steering, throttle. So to accurately follow the planned trajectory, decision frequency is milliseconds. So that is true that low-level controls are basically the ones that actually are defined by the brakes, throttle, steering. So these are the ones that are very dynamic in nature, and it totally depends on the trajectory that you are choosing. So the way you choose your trajectory, it actually defines and governs your complete or entire system on how you are actually uh, controlling the complete path in a proper manner. Okay. So that is how you define it and govern. So now comes the next one. Evolution of vehicle automation. It is an overview of it. So this actually defines how throughout the journey of this complete automation procedure, how your entire vehicle which started to come up with an idea of automation actually developed. So in the very early stages, it wasn't. It was just a vision or a thought which was given, which actually tells you or basically helps you understand that what was the criticality or that time no criticality was there. It was just the need or it was just a base of hobby grade project that was taken up by the scientist at that time. He What if the driver becomes a another passenger and the complete vehicle just moves from point A to point B by itself? So it became a thought into the mind of people, wherein people thought this would be a very brilliant idea that the system would be completely automated and person has to sit. But then came the challenges also with it, because with every new technology coming into the market, it comes with pros and cons. So, I won't say cons, but yeah, there are challenges to control it because there were a number of things, and at that point in time, there were other defined things that were not present in the market. So, the development became very slow. But if you see today, there are companies which are being supported by the auxiliary companies to provide a vision, um, computer vision to the automobile, and then thereafter it becomes very easy for the people in the mainstream to actually develop an idea because they have all the utility uh, things in the market which available with them. So yeah, that was the thing. The journey towards fully autonomous vehicle has been a gradual progression marked by significant technological advancements and shifting paradigm over several decades. So yeah, it was not a thought that was that actually came up in the mind of people and it became an idea. So it was an idea for a longer period of time. People were actually working continuously onto this idea, and then uh, there was a time where this idea became a technological development where people helped. Uh, a lot of people were working towards this mission, and they made it a reality. So that is true. So the 1950s to 1970s was a very early vision where this was just an idea coming into people's mind, and there were theoretical concepts and initial automated highway system proposals laid the groundwork. So basically, just a minute, I'll come. Just a minute. So yeah, so that was the case, and uh, so yeah, in 1950s to 1970s, it was a very early beginning where theoretical concepts and initial automated highway system proposals laid the groundwork. But yeah, that was not the case. It always starts as an idea, and thereafter, once the idea is being populated with different people's thought processes, it becomes there comes a prototype of it, and then comes the MVP. Lot of initial level starting MVPs, and then comes the final product from it, and then that product becomes a reality into uh, that prototype becomes a reality. So it doesn't happen only on a single day or two. It takes a lot of time and effort to actually build a system which is worth it. So, a lot of credit to the people who started the very start of this automation process. Then, from the 1980s to 2000s, there was the ADAS Foundation, that was an Autonomous Development Association foundation, that actually had an introduction of features like ABS, that was automated braking system. The cruise control. So cruise control means when your vehicle is moving on forward direction, it has to from A to B actually move at different speeds at different point of time, right? So at most of the time, the cruise control part, you need to actually function in such a manner that your cruise will be fluctuating from point A to point B at different instances. So that cruise control is being controlled electronically. It doesn't happen that that cruise control becomes a habituated thing. It becomes an electronic thing that gets fluctuated and controlled by itself. So that becomes the second part. Third is an early sensor integration began the ADAS era. So the sensor integration actually began the very initial position. So yeah, I told you that the ADAS is actually the ADAS actually is governed by different series of sensors, right? It doesn't happen that only a single sensor is required for the complete functionality of the uh, of the automation vehicle, autonomous vehicles. So there are different sensors and a different period of time they were evolved. So it didn't happen that only at a single uh, point everything evolved around time. So it was a complete gradual process that actually took years and years to actually evolve. So then that happened during a period of 1980s to 2000. Then, yes, one minute. Yeah, then came the 21st century, where actually which was actually defined as the prototype era. So in the early 20th to 21st century was the prototype era where you did the sensor, you get the idea, but then people were working to make it a reality. So then DARPA. So DARPA is basically the DRDO of US. So as people uh, from DRDO are working closely with the army, and they make certain products that actually facilitate or ease the technological development that is required by the army and being fulfilled by the army. Similarly, DARPA, uh, DARPA is so DARPA is the US version of the same, wherein it's a government body that actually closely works with the army and government to facilitate and ease the technological development. So they did a tremendous amount of work during the early period, and they have quite brilliant scientists that are in the world today uh, working on to certain projects. So yeah, they are quite superb. So they were the ones who actually took the prototype era to the next level, wherein DARPA actually challenges spurred rapid development. First, self-driving prototypes emerged from the research lab. So they have their own research lab where, uh, so yeah, Vishal, I'm audible, right?
Yeah, yes, sir, you are audible.
So yeah, then actually this rapid development was first facilitated and eased by the research labs that were present, used by DARPA, and they helped you in understanding the complete cycle of prototype, and that happened in the early 2000s, from 2000 to 2010. Then the 2010 to the present generation, that is present time, that is 2025, was a commercial pilot project test where companies like Tesla and also majorly Tesla, BYD, and Toyota, and some point to Mahindra. And these companies, having their own research wings, came into the market, and Tesla leading by an example. Uh, they actually came into the picture, developed their own prototype, private companies, doing a lot of testing, giving final and tremendous amount of good results into the market where they actually helped you in uh, completely finalizing the entire product line, and they are limited to commercial deployments, ride-hailing services, and extensive testing in specific operational design domains. So, and extensive testing in specific operational design domains. So, ride-hailing services. So, basically, they tried capturing different segments. That was that when you want to move from point A to point B, you actually book a cab, and the driver comes and they actually take you from point A to point B. But in the ride-hailing services, doing an autonomous test, you book a cab, the cab comes, but it is driverless, and you sit and you go to point B. So that is how the commercial piloting happened, and an extensive testing in specific operational design domains. So Tesla actually in this era had a lot of testing facilities that actually help you in building your own design in a proper and sequential manner. So Tesla actually laid the foundation for the same. And yeah, today a lot of companies from India also are actually working on the same idea. And that is possible because a lot of other sister companies have also come into the market supporting the mainstream companies. So like the sensor companies, the camera companies, the computer vision companies, the robotic company, the motor company, the ESC company. So these companies actually clubbed together, and then proper foundation or a network of companies came together and clustered to make the product work. So it was not something that Rome was built in a day. So similar to that, the autonomous vehicle was not built in a day. It is still under development, and people have been working from almost a century onto this idea. Not if not a century, then at least 50 years working on this idea to make it a reality. And people are doing a fabulous job into it. So then comes the future, that is created deployment. So focusing the ship, basically in the pilot stage, there are hybrid kind of things wherein you can put it on autopilot and then wherever needed to change the lanes. That we discussed in the last class. Wherever needed to change the lanes or wherever needed to actually shift to different control modes. there you take the control to the physical driver, and then you actually facilitate that change. So that is how it happens, and it happens in the regular basis. So focus shifts to expanding coverage, standardizing regulations, and achieving widespread adoption. So the adoption comes only when people have trust. So product becomes popular not by its better better marketing, but it's better marketing is needed. But before that, your technological development, that is PD, should be done in such a manner that you are building that idea with minimalistic challenges and maximizing the complete output. So that is how you build your idea. Uh, that's what. So that's for the for future of scale deployments. That is to focus shifts to expanding coverage. So coverage should be more standardizing the regulations. So as you do the testings, as you do a lot of testings, you make regulations, follow certain norms, which will be followed by different companies in the mainstream media, and then achieving widespread adoption of it. So this high level timeline sets the stage for a deeper dive into key eras and milestones that have shaped the vehicle autonomy. Okay. Then comes the early milestones. So pre 2000 era, what was the situations and what was people's situational awareness and how this paradigm got shifted and transformed into a very fabulous idea. Okay. So so the foundation for modern autonomous vehicles was laid decades ago through pioneering concepts and gradual integration of electronics and sensing technologies to driver assistance systems. Okay, so let me take it this way. So you see, in the early milestone sections. So what happened was different companies, as I told, clubbed together. Okay, and after this clubbing, what happened was people started accepting this technology as a developed idea. So I'm writing also at the same time. So maybe that is the reason why. So I'm actually writing as well. So that is the reason why. Mm. But yeah, I cannot relate this. But yeah, it's fine. So yeah, this clubbing of the things actually just a minute, just a minute. You can hear me, right, Vishal?
Yeah, yes, sir.
Okay, so yeah, that was the key development that was so this acceptance of technology happened with the different companies that were built came together, and that looping mechanism actually helped you in developing the ecosystem in a proper manner. And thereafter, this complete scenario of economical development actually resulted into different sensor companies, different camera companies, electronic sensing, uh, and the driver systems. These clubbed together, and this autonomous vehicles thing became a reality. So people's effort actually happened in this manner that people were ready to accept this change in a positive manner and they supported. So every time a decision or a design becomes successful only after people in the market are very much adaptable to certain acceptance. So they are accepted. So these technologies are accepted. So not only a better idea can actually make it popular, a better idea can definitely be a very much what do you say, the salt in your curry to make it a working thing. But then comes the marketing and people's adaptability and ease. So there it comes as a challenge because, for example, so take two different products. Okay, so take for example, take this thing. Take your supposedly you go and buy clothes. So you go and buy a shirt. So that time what happens is like you see different shirts in the market and you prefer the one that is branded, right? So always it happens that you tend to move towards a product that is trusted, more popular, and it is accepted by people in the market more, right? So it doesn't happen that you are actually attracted to something that is not workable. So it always happens that you are tend or inclined towards something that is more popular in the market. So that is something that is actually needed for you to do. So that was the thing that early milestones in the pre-2000 era work and how it works. So the foundation of modern autonomous vehicles was laid decades ago through pioneering concepts and the gradual integration of electronic and sensing technologies into driver assistance system. So experimental automated guidance. So this was the first point that actually got developed in the pre-2000 era, where early research explored theoretical concepts for automated steering and navigation, often of dedicated highway systems, setting the intellectual groundwork. So early research was actually making a groundbreaking intellectual base for uh, the automated steering and navigation for dedicated highway systems and setting the intellectual groundwork. So early research explored theoretical concepts for automated steering. So automated steering was developed at that point and navigation also with that GPS. So people started sending satellites in the space, and that sending of satellites was being leveraged by the autonomous vehicles as well because they actually needed the navigation part very much often and very precisely to be discussed and designed. So often for dedicated highway systems, so in the highways it was needed because to actually navigate the proper channel in a systematic manner. Setting the intellectual groundwork. So you can see here in the image also that this is the ground vehicle, this is the autonomous aerial vehicle. So these are the things that these are the sensors and technologies that were needed for complete functionality of the system. So that is how you actually process it. So the second part is precursors to cruise control. So cruise control also played a very important role. As I say, if moving from point A to point B, it becomes a challenge for you to uh, actually kind of understand how to actually mark your cruise or how to vary your speeds at different instances of time. So uh, when you move from point A to point B, you actually fluctuate your speeds at different instances. You get some crowd, you get some traffic, you get some easy way. You move your speed high, you get your speed low. So that is how you actually fluctuate your speeds accordingly, and your precursors for cruise control happen in that manner. So initial systems focused on maintaining constant vehicle speeds, paving the way for the development of adaptive cruise control functionality. So key controlling parameters for the cruise control happens in that manner, wherein your vehicle's constant speed is being paved for the way for developing of rapid cruise control for functionalities. Anti-lock braking system. So this is the third part, that is the ABS system. The introduction of ABS marked a significant leap in electronic driver assistance, enhancing vehicle control and safety during the braking. For example, I will tell you. So, this ABS system, that is anti-lock braking system, this became a very key parameter for actually governing your complete, what to say, your motion. So, your ABS became a challenging part in completely dominating the vehicle's automation because if your braking system doesn't happen systematically good, uh, then your what to say, nothing gets functional, right? So if your uh, uh, this thing, if your braking system becomes bad or it becomes challenging for the people around you, it becomes a safety concern as well. So if uh, you're moving from point A to point B and your braking system only doesn't function properly, so how will the people be reacting to it, and uh, how is the trust going to be built, right? So trust is only getting built by people, and so that is called acceptance, right? So acceptance is the key parameter and gets controlled only by your quality of the product and your scale of marketing as well. So if you make your product in your room and you don't market it, how will the people come to know it? So that is how you actually make it a functional thing wherein you pitch different products in a proper manner and do it properly. So that was the third part, the anti-lock braking system, ABS. Fourth is the early cruise control adoption. So by the late 20th century, rudimentary cruise control systems became available in production vehicles, uh, offering drivers basic management assistance. So speed management assistance became a very much key parameter in the loop to uh, actually make it a uh, habituated thing wherein you by the late 20th century you get a basic crude design of the cruise control part. Um, you make it you make it break it till you make it. So that is true. So you do it, do the prototype, test 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 it. You make it such accurate after a certain point in time that you're and also with the development of different sensors in the market. So after these things uh, became a habit and adapted with people. So this cruise control became so mature enough that even in normal vehicles also there is a automatic cruise control now, wherein you put that cruise control and you just need to control the brakes and accelerator and everything, brakes and all, your and steering, cruise control accelerator part will be taken care of, right? So that is how this thing is also governed. Now comes to modern era. So the modern era is between 2000 to 2010, wherein the truth of a millennium enshrined in a decade of rapid advancements, solidifying the foundation of modern autonomous vehicles research and development. So that is true. So during the modern era, between the period of 2000 to 2010, this complete technological developments of milestones became a very much prototyping era, wherein you do the prototype, test it, and then you get the feedback of the results and you mature the product or you mature your prototype. So that became a very much constantly cyclic loop wherein you do your tests and you develop your prototype and then you make another series of prototype and then you test it again and make your product mature. That is how your product development happens. So there are certain ground challenges to it and there are certain Uh, Reality that you need to face that in market, everybody is not going to switch to the autonomous era very soon. So your sensors need to be very much accurate enough to actually capture what is happening around you properly and then give a feedback according to it. So the modern era between 2000 to 2010 happened in that manner, wherein your the turn of the millennium ushered in a decade of rapid advancement, solidifying the foundation of modern autonomous vehicle research and development. So technological milestones. This period saw the widespread adoption of the refinement of critical driver assistance systems that now serve as a building block for higher level of autonomy. So that is true that all the things that were done in the yeah, please say whatever you want to say. You raise your hand. Can you please message or you speak? Vishal, did you raise your hand or somebody else? Hello? Vishal, can you hear me?
Yeah, yes, sir.
So somebody raised uh, the hand. So can we collect the question for the next 5 minutes and then maybe proceed?
Yeah, okay, sir. No one is
Okay.
raised hand actually. Okay, sir, continue
Somebody,
with session.
okay, I shall continue, right?
Yeah.
Okay. Okay. So, yeah, this period saw the widespread adoption and refinement of critical driver assistance systems that actually now serve as a building block for higher levels of autonomy. So yeah, that is true that initially what all things were actually developed and decided that these things will function in that manner. That is how your complete autonomy of the things are built, right? So um, this period was a transitional period where you do your there were different sister companies that were also getting built up, and at the same time, there was an era of complete dominance of the same, and that is how your things would look like. So, this was the period of that era transition. So, people, whenever you put certain new technologies in a government office, so you can see people neglecting it. "क्या रे यार, हम नहीं करेंगे, we won't accept it." But then when people start to realize the use of importance of it, they start then they start to slowly accept the things properly, right? So that is not how it is actually governed in that manner or that fashion. It actually happens by itself, and people around are actually very much vigilant about the same. That they are not truly taking care of the same in a proper manner. So, this period saw a widespread adoption and refinement of critical driver systems that now serve as a building blocks for higher levels of autonomy. Electronic stability control, that is ESC. So, basically, ESC is electronic stability control, or you can say an electronic speed controller. So, speed controller actually, that is what I was telling that along with the motor, there comes the ESC because then your cruise control and everything becomes a critical parameter that we are going to analyze maybe in the next class or next to next class that we'll be doing the analysis. So therein we'll be discussing the cruise control and how this cruise control is actually functional. This is important. So this ESC becomes very much important enough to help you understand and mark the significant importance of the speed controller unit because if you select a motor, you get a certain amount of torque. That torque needs to be generated by the speed or the RPM of the motor. So that is getting regulated by the ESCs. So if you don't give a proper command or a proper channel to the ESC for a proper feedback mechanism, then I don't know what will happen. So you can't control can't get the proper torque, you can't get the proper speed, or can't function with the proper RPM. So and this is it. So then comes the adaptive cruise control (ACC). So moved beyond basic speed control to automatically adjust speed based on traffic using radar technology. So that's what we discussed in the last class about the different technologies in the market. So one was the radar technology that was very much prevalent and important because the cruise control, the traffic system, everything is getting monitored live. So it is a local parameter as well as a global parameter for mapping as well as trajectory planning. So both the things. Uh, that is how just a minute. So move beyond the basic speed control to automatically adjust the speed based on traffic using radar technology. So advanced sensor integration. So greater use of radar, early LiDAR prototype. So LiDAR is actually basically to understand what is there next to you. So for object collision avoidance. So LiDAR is basically to understand the collision avoidance techniques of system. So it helps to understand the uh, yeah, so yes, yeah. So yeah, this was the adaptive cruise control and advanced actually the use of greater use of radar, early LiDAR prototypes, and improved cameras began to inform vehicle decisions more comprehensively. So that is true that I told you, right, that the different sensors we clubbed together, and these sensor companies actually made an effort to actually work it out. Thereafter, it became very easy for everything to get collaboratively prosper. So if you don't have one thing in the market, you can't make another. So that is how one thing complement other, and this is how your things are built. So, however, the most significant catalyst of modern AV research came from a series of groundbreaking competitions. So that is true that this these F1 competitions that happened. So these actually help you understand the urge and the need for these challenging events, how to win them because you get dopamine, right? Every time you win it, you get a dopamine release. So that is why there is a concept of getting first in the class or being first to do this. Because if that urge of challenge is not there in the people around you, that won't function and prosper properly. So uh, that is how your things are built also. So uh, these competitions actually played a catalyst into it and helped you in developing the things very fast. So then comes the DARPA challenges, the grand challenges, where Defense Advanced Research Projects Agencies, DARPA, hosted robotic car races that dramatically accelerated innovation in autonomous driving. Okay. In 2004 and 2005 grand challenges, teams completed to navigate uh, 240-kilometer desert course. Uh, the 2004 challenge had no finishers, but the 2005 event saw Stanford Stanley complete the course, making a pivotal moment. So yeah, that is true. That initially when that competition was done in 2004, people were still coming out of the old era, and they were accepting the modern era of autonomous vehicles. But then that competition played a very pivotal role in 2005 to actually help Stanford in completing that race. Okay, and win that competition comprehensively. So that is how your things are built. Then the knowledge is being shared across people in the globe, and then that significant research is developed. Okay. Then comes the 2007 urban challenge. So this challenge actually required vehicles to obey traffic laws and interact with other autonomous and human-driven cars in a stimulated urban environment. Uh, Carnegie Mellon's boss took first place in Boston in 2007 urban challenge. The turning point, these challenges were crucial in pivoting the feasibility of autonomous navigations and fostering collaborations among academic and industry researchers. Okay. Then comes the commercial and research acceleration. So that happened between 2010 to 2020. Huh. So this pivotal decade saw autonomous vehicles and just so this pivotal decade saw autonomous vehicles development transition from academic pursuits to serious commercial investments and real-world trials driven by significant technological breakthroughs. The major investments started coming into this decade. People started investing and trusting this kind of an idea, and also their sister concern companies became growing to a certain extent more than what they have ever seen before. So that showed a clear-cut trust that people started having into this evolving, uh, what to say, evolving concept and technology. So major investments, tech giants like Google, Waymo, and traditional automotive manufacturers such as General Motors, Cruise, pour significant capital into AV technology, establishing dedicated autonomous driving divisions and research facilities. So yeah, people started investing into these kinds of concepts, and they started trusting into the new technologies and ideas. So then comes the commercial pilots. So the first commercial pilot programs emerged deploying self-driving cars for ride-hailing services in select cities and operating autonomous shuttles in controlled environments, moving beyond pure testing. So then comes the deep learning breakthroughs. So advances in deep learning and neural networks revolutionized perception systems, enabling vehicles to more accurately identify objects, classify road conditions, and predict behaviors in complex driving scenarios. That is true. So companies like Uber and all started accepting these kinds of uh, multilingual and different countries. They started accepting and challenging themselves, starting their own pilot projects, wherein they have started doing collaboration with different kinds of industries and making autonomy a normal habit. Now comes the recent trends, that is from 2020 to present. What was it? So just I think we'll complete this slide today, and thereafter we have one more slide. Let me show you that as well. So that slide, flight mechanics slide, the one that we're going to discuss after this. Just a minute. I'll show you in the last part of the class. So, so now in the recent trends from 2020 to present, the current era of autonomous vehicle development is characterized by a pivot from uh, unbridled ambition to strategic, safety conscious deployment and commercial viability within defined parameters. So that is true. The current era of autonomous vehicle deployment is characterized by a pivot from unbridled ambition to strategic, safety uh, cons- conscientious deployment and commercial viability within defined parameters. So that is true. So first is safety first approach. So where developers are prioritizing rigorous safety validations and carefully managed rollouts with specific uh, GoFence operational, geofence operational designs, um, domain to ensure reliability and foster public acceptance. So there are two major uh, key terms here which needs to be discussed first before moving further. First is the geofencing. Second is basically first we'll discuss geofencing. So what is geofencing? Uh, basically public safety becomes a very key parameter. So during the testing phase, you see Tesla vehicles getting crashed like hell, and people inside it are facing different injuries as well. So that is a part of the testing, but instead of that, people can use sandbags as well to, if it is a complete autonomous thing, so that thing cannot be or a robot. But people haven't reached to a certain extent in that sense, so they are still using human. They are still in search of people doing that testing. So geofencing plays a very key parameter. So when you actually put geofence around the periphery of your autonomous vehicle, you define the radius around which it can go. So around that radius, you can plan your mission, and then it can go from point A to point B, define that is under the geofence radius. Okay. So geofencing is nothing which I will show you here. Let me show you. So suppose this is your geofencing. Okay. Let me do it again. Suppose this is your geofence. Okay, this is geofence. Okay. Now suppose this is your car, right? And it's a bad car. But please bear with it. So now it is an autonomous car. This is an AV. You plan your mission from point A and you need to go to point B. Okay. So this geofencing, what it does, it makes if your mission is within the geofence, it will not do any problems and it will go from this point and it will reach back to you. But if your geofencing point A is here and a point B is here, you go from here, you try to go here, but then it is above outside the geofence, so it will come back. Okay, it will come back. So now what happens is uh, um, complete thing is getting controlled by the geofence now. So chances of accidents that are happening becomes minimal. Okay, and when it tries to go outside it, it tries to go outside it, it returns back to its original position. Yes. Okay. So then comes the second part, the targeted commercialization. So commercialization efforts have focused on constrained and predictable environments, leading to successful deployments in areas like last mile delivery, industrial logistics, and public transportation shuttles, evolving regulatory landscape. So governments and industry bodies are actively collaborating to establish comprehensive regulatory frameworks, safety standards, and testing protocols essential for widespread and responsible AV deployments. Okay, so that is the third point. That is evolving regulatory landscape. That is, your governments and industry bodies are actively collaborating to establish comprehensive regulatory frameworks, safety standards, and testing protocols essential for widespread and responsible AV deployments. That is true. Now comes the next one. So this is the current driving automation thing. That is SAE levels of driving automation. So the SAE J3016 standard defines six levels of uh, driving automation from no automation to full automation. This globally recognized taxonomy is critical for clear communication, guiding regulatory frameworks, and standardizing design and testing protocols across the industry. So, level zero, uh, no automation. So, there the human driver performs all driving tasks. So, there nothing was done by the automation thing and everything is being controlled by the pure driver thing. So everything is being controlled and operated by the driver. Second comes the level one driver system. So system assist with either steering or acceleration, braking, example adaptive cruise control. So in the level one of the autonomy part, there comes different assisting parameters. So driver is being assisted by different functionalities that are being performed by the uh, system. So system levels assist set certain way of steering or acceleration or braking, that is adaptive cruise control is being performed by the assistant in the automation part. Level 2, that is partial automation. So here level 1 was not automation, but it was just an assistance. So in the cruise control, if you put it on the cruise control, so I told you right that in today's world, cruise control has become a very much accessible option that people are using for certain in certain ways. It was being used from a longer period of time, and today it has become a common thing in all the vehicles, be it autonomous vehicle. Or not. So cruise control is basically something that is taking care of your accelerator, how much you want to speed up, how much you want to reduce. These things are being cared by that. So level two becomes a partial automation. So the system assists with both steering and acceleration braking. So human supervises environment. So here the human becomes a supervisor. So here what happens is like So, yeah, in the level two partial automation, system assists with both steering and accelerator option. Human supervises them. Level three. So in the level two partial automations, a human becomes a assisting member, and major of things like cruise control, steering control, everything starts happening by the by the automation thing. So this becomes a key parameter in the controlling mechanism. So now comes the level three control conditional automation, wherein uh, your vehicle handles most driving thing, and human must be ready to intervene when prompted. So this is the part where your human become secondary auto secondary co-pilot to the drive to the main autonomous driver, wherein everything is being controlled by the driver. But in case something doesn't work, and it stops working, so that time your driver takes control, and that mechanical control is being switched again. There is an option. So now comes the level 5 full automation. Vehicle performs all driving tasks under all conditions without human intervention. So in that, the driver is actually a passenger, and all the key driving tasks are being performed by the vehicle only. So there is no need to actually uh, take care of the driving parameter anymore. So the driver takes care of everything and everything. Sorry, your vehicle takes care of everything and everything. Your driver needs to drive. Okay. Um, okay. So Vishal, I can hear me, right?
Yeah, yes, sir.
Now comes the level 0 and 1 foundational automation. So, understanding the initial stages. Just write this slide show. So, level 0 and 1 foundational automation. So, understanding the initial stages of automation clarifies the baseline uh, for more advanced systems and the driver role in each. So, yeah, both the automation levels, that is level 0 and level 1, there is 0 is the no automation part, and 1 is the driver assistance part. So in the level 0 automation, no, that is no automation. In level 0 vehicle, the human driver is completely in control of all the dynamic driving tasks. The vehicle offers no automation to assist with steering, braking, or acceleration. So the driver is solely responsible for monitoring the driving environment and operating the vehicle. This level represents motor vehicles on the road without any advanced driving assistance systems, that is ADAS. So in this, the advanced driver assistance systems are not present. So in this level, everything is being controlled by the driver itself. Now comes the examples. The examples include vehicle equipped on only with basic cruise control and anti-lock braking system. So there are a few things that are there into it. That is the cruise control part or the brake anti-lock braking system part. That is the ABS. So these are things that are by default. So these doesn't come under automation. Automation is actually when your brake, your steering, and all these dynamic parameters gets starts controlling by itself. Okay. Hmm. So that covers the no automation level zero part. Now level one, that is the driver system, where level one systems provide specific assistance for either steering or acceleration and deceleration, but never both simultaneously. The driver must continuously supervise both the system and the driving environment. So adaptive cruise control, that is ACC, automatically adjusts vehicle speed to maintain a safe following distance from the car ahead. So lane keeping assist, that is LK, that provides subtle steering inputs to help keep the vehicle centered within the lane markings. Driver responsibility remains paramount. These systems are aids, not autonomous functions. Level 2 partial driving automation. So at level 2, the vehicle independently controls steering, acceleration, and deceleration. However, the human driver must constantly monitor the environment and be ready to intervene immediately as the system provides only partial automation. So, in the level 2, there is the partial automation, but the driver is actually actively involved and whenever required can take control to actively get involved into the process. So that is how your driving methodology is being controlled here in the level 2 driving automation system. So Tesla Autopilot. So that's what I told, right? That the Tesla Autopilot is becoming a very key and the major uh, part in the development procedure of the uh, entire automation that is happening throughout the globe. And this plays a very pivotal role into completely self-sustaining the entire system into the market, and then thereafter keeping a very closely attached cruise control methodology. So Tesla was a very, you can say, a torch bearer into this automation industry in the private loop, wherein this automation starts to happen whenever there gets big players involved. So Tesla was not a big player at the start, but uh, the kind of development that Tesla started doing at the later stage of its development automation actually made it a torchbearer, and then thereafter it started to do cruise control, then started to do auto steering, then brake control, accelerometer, everything it started to do by its own. So there happened to be certain failures also during the pilot test that led to certain haphazardous situations, but yeah, and that is not forgettable and that is not forgivable as well. But they are now in a very better state wherein they can do. But yeah, that is not forgettable and forgivable. They are doing it now in a better way, methodology and more. Yeah, that's true. Yeah, Sheikh Honey, it will be sent by the concerned person from XLRT, and he'll take care. You wait for some time. Now comes the Cadillac Super Cruise. So offers hands-free driving on compatible highways. A sophisticated driver monitoring system ensures the driver remain uh, prepared to take over. So this becomes very important, wherein your entire system that is shared, so you can fill it. So offers hands-free driving on compatible highways. A sophisticated driver monitoring system ensures the driver remains attentive and prepared to take the control over. Okay. Now comes the level 3 conditional driving automation. So at level 3, the vehicle's automated. Hmm, just a minute. So yeah, so let me do this. So in the level 3 conditional driving automation, at level 3, the vehicle is automated Driving system manages both environmental monitoring and dynamic driving tasks under specific conditions. However, the human driver must remain available to intervene promptly when requested by the system. So that is true. That in the complete autonomy case, wherein your things are very much in control, the automation as well as the environmental monitoring and dynamic behavior is being controlled by the vehicle itself, uh, and the vehicle starts assigning the tasks based on its requirements. So it doesn't happen that now it happens through another means. It happens from the driver itself. So that is there. Now, the mm, so this includes system engagement, request to take over, human takes control, and driver acknowledgement. So this conditional autonomy uh, presents unique challenge related to uh, driver attention and handover readiness. So that is true that anytime and every time it doesn't happen that the driver needs to take control, but the driver has to be in the active position wherein whenever needed, it takes control over the entire charging system and do the autonomy part in a proper manner or a channelized manner. Now comes the level 4 and 5, that is high and full driving automation. So as we ascend the SAE-J3016 hierarchy, the role of the human driver diminishes significantly, culminating in systems capable of handling all driving tasks without human intervention under specified conditions or universally. So that is true that uh, as we ascend the SAE J3016 hierarchy, the role of the human driver diminishes significantly, culminating in systems capable of handling all driving tasks without human intervention under specified conditions or universally. So, yeah, human intervention in the level 4 autonomy is actually um, there, but very minimal. So, it is very, very, very highly improbable thing that it should happen. But yeah, there is still a scope of hope and chance, not hope, but a chance that he has to take the control. So he has to be attentive. At level 4, the vehicle can perform all driving functions and monitor the driving environment independently, but only within a specific predefined operational design domain, ODD. Within this ODD, human attention is not required. If conditions exceed the ODD, that is the operational design domain, uh, the vehicle can safely pull over or prompt for human takeover. So that is true that whenever you see that the geofencing or anything that you have kept as a safety parameter check gets failed, then that is the point only then it is required that your driver needs to take over the thing. Otherwise, it's not needed. Okay. Just let us take a break of 2 minutes and then we'll resume. Yeah, so now from the level 5 automation, and that is the point where the drivers are not needed anymore, even at very much critical circumstances, and your uh, autopilot takes care of everything. So, level 5 represents the pinnacle of driving automation. These vehicles are capable of performing all driving tasks under all road conditions and environmental circumstances were equivalent to a human driver. No human interventions is even required, and the vehicle can operate without a steering wheel or pedals. While the ultimate goal, the level 5 automation is still largely a future prospect and has not yet been achieved at a scale of general public use. So that is true. That is when you talk about a full automation of the vehicle, so this is still under progress and it will take a lot, at least uh, few years, at least a decade, it will take for the testing and everything. And it is a future product project to actually make this thing a reality. And it won't happen very soon in a couple of years. It will take some time. So, but yeah, the full automation, full autonomy thing is under progress and that will be built. Now comes the human factors and safety considerations. So, ensuring the safe and reliable operation of autonomous vehicles requires a multifaceted approach addressing both human interaction and system level redundancies. Human in the loop challenges, that is driver monitoring, critical for ensuring human vigilance in partial L2 and conditional L3 automation, detecting distraction or incapacitation. Okay, so that is the one that is being required. So that is the human in the loop challenges that so these are the safety challenges and uh, considerations that needs to be taken. So first one is the driver monitoring that comes under L2 and L3 automation conditions, this detecting the distraction and incapacitation. Hand over strategies. So designing intuitive and timely mechanisms for the system to request and the driver to assume control, especially in L3. So trust and misuse. Managing driver expectations to prevent reliance leading to inattention or under reliance leading to disengagement. The next part is the full autonomous automation safety pillars. So redundancy, incorporating backup systems for critical components, sensors, computing actuators to prevent single point failures. Fail-safe design, engineering systems to revert to a safe state, example minimum risk maneuver, if a critical fault occurs. Operational design domains, ODD, clearly defining and operating within specific environmental, geographical, and temporal conditions where the system is validated to be safe. Safety engineering spans software, hardware, human factors, and operations for forming the bedrock of autonomous vehicle deployments. That is true. So everything becomes a very key parameter in keeping everything into loop and doing the things properly. So human in the loop challenges and full safety, full automation. So human factors and safety considerations, which include human in the loop challenges, full automation, safety pillars. So these are things. Now comes the yeah, societal drivers for autonomous vehicles. So the push of autonomous vehicles is fueled by several compelling societal benefits, promising a transformative impact on how we live and transfer. So enhanced safety is the first point, where over 90% of all road accidents are attributed to human error. Autonomous vehicles aim to drastically reduce this statistic through consistent, precise driving, saving countless lives and preventing injuries. Now comes the reduced congestion. So coordinated driving patterns and improved traffic flow can dramatically decrease commute times and all elevate urban congestion, making cities more livable and productive. Increased mobility access, providers unprecedented independence for the elderly, disabled, or and those unable to drive, fostering greater social inclusion and participation in community lives. Environmental benefits, smoother acceleration, braking, and optimized speeds lead to lower emissions and improved fuel efficiency, contributing to a cleaner environment and reduced carbon footprint. Economic efficiency, optimize routing, reduce fuel consumption, and lower insurance premiums contribute to significant economic savings for individuals, businesses, and public services. Okay, so these drivers highlight potential of autonomous technology to address some of the most pressing challenges in the modern transportation. That is true. Now comes the application. So logistics. Applications are logistics and goods movement. Applications are logistics and goods movement. So autonomous vehicles are poised to fundamentally transform the logistics and goods movement sector, offering solutions to long-standing challenges and creating new efficiencies across the supply chain. So platooning and hub to hub, that is autonomous trucking, platooning and hub to hub, yard automation, last mile robots and drones. That is true. Now comes the question and answer part. So uh, we have explored everything, these technological benefits, and um, I would actually want you guys to now help me with this thing and ask questions for the last 3 minutes or so. So I would mic drop and I would ask you to come forward and ask some questions from. So there are 3 minutes for you to do it. And if you are okay with it, you can post it in the group and rest we can close the session and do let's meet tomorrow. So open for questions. Any questions? Uh, People around? You have any questions? If not, we can close the session. we can close the session. So, Vishal, are you there?
Yeah, yes, sir. Yes, sir. Thank you. Thank you for the wonderful session, sir.
Okay. Thank you so much.
Yeah. Dear students, kindly make sure to mark your attendance without any fail. Again, I am sending the link in chat box.